was telling the other day, we will now handle problems where the constants, so far the problems that we had done were either maximization or minimization types, but the constraints were all less than or equal to types. Okay, so that we only had to talk of slack variables in each constraint, we had to add in, and then these slack variables themselves gave us our initial basic physical solutions, right? And we could go ahead with the simplex algorithm. Now, supposing you have a mixed set of constraints in the sense that you have less than or equal to types also, you have more than or equal to types also, and you have equality types also. We can come across situations where the constraints are exactly equality types. So in these cases, you will say, see, what does these inequalities represent in constraints? Each constraint is representing a resource. So basically, we have on the left-hand side the availability of these resources, and on the right-hand side is the utilization, right? So whenever we have availability less than or equal to utilization, that means there is a slackness in that particular resource, and therefore we add that variable. Whenever there is a more than or equal to type signs, that means you are using in surplus. So that is why we have to subtract it. The moment we have equality, that means whatever is available, you are utilizing it. Okay, so that is why, as such, nothing should be added and nothing should be subtracted. Okay, so in such constraints, what do we do to get the initial basic physical solution? Now, because we have seen the simplex algorithm and we have also observed that the algorithm works best provided we take our b as I. Okay, so that means we need the coefficients in our constraints to be such that we want some of them, especially the rank, whatever is the rank, at least those many of them we want to correspond to the identity matrix. So that means their coefficients in the constraints should be just 1 or 0 each, right? So 1 exactly in one constraint and the remainings, they are all 0. So to get these initial basic physical solutions, in the case when we cannot have slack variables, or in the cases when we have either surplus or something, or equality types, we bring in the concept of what we call as the artificial variables. Okay, so as the name itself says, they are variables but artificial in nature. That means they are not true variables. See, we so far we have talked of decision variables, and we observe that these decision variables exist physically because our decision is going to be based on the values which these decision variables are going to take, right? So they're physical, they exist physically, they contribute to the objective function as well, because the coefficients of the decision variables define the objective function, which is either to be maximized or to be minimized, right? Similarly, we had slack or surplus where we observe that they do not have any physical significance as such. That is why they do not contribute to the objective function values, but they have their own economic significance because every slack or surplus variable can give us some information on the corresponding resource to which they correspond to. But when we say artificial, that means they're totally artificial in nature. They have no physical significance, they have no economic significance as well. So that means we are incorporating these variables only and only for the purpose of getting an initial basic physical solution. We do not want anything else to be done from these variables. So that is why we are calling them as the artificial variables. Now, that means if we are incorporating them only for the initial basic physical solution, then the moment we move on to the next iteration, then what happens? Maybe, they are the basis, first of all, in the table 0, because they form the initial basic physical solution. So the moment we move on to the next iteration, that means one of them leaves the basis and some other. So some other could be from the set of decision variables, some other could be from the set of slack or even surplus variables. right? Now they can enter, right? But that means the moment an artificial variable leaves the basis, its role is over, its job is over. We don't need that anymore. Okay, so that is why the theory with which we handle simplex algorithm in the cases of artificial variables is developed in such a manner that artificial variables, once they leave the basis, can never re-enter the basis. Okay, this is, there is a proof behind it. We don't have to do it here, but yes, it has been proved that artificial variables, once they leave the basis, they will never re-enter. Okay, so once they have left the basis, then we can remove their column from the simplex table as well, because we don't need them anymore. They are not going to enter back the basis. So their job is over. Their job was only to start the solution procedure, which they have done. Okay, so to handle artificial variables, we have two basic methods. One is called as the, it is also called as the Charnes Big M method, okay, because it was given by Charnes, so that's why it's still called as the Charnes Big M method. And the other method is your two-phase method. So these are the two methods on the basis of which we handle artificial variables. See, that means, see, even if Charnes gave this technique, he gave this technique only for artificial variables, right? So that means nowhere down the line have either of these methods changed the simplex algorithm. The simplex algorithm still remains the same. Your table will still remain the same, but it's just that this is an addition to the simplex algorithm that we were handling with so far. Okay, so what we do here is, like, again, say, let's start with the problem, and then I'll gradually explain how to handle. We'll do the big M method first, and then we'll move over to the two-phase method. Okay. Now, what we do is, like, for example, say, supposing you have to maximize Z equal to, this is your exercise problem 4.1. So if you want, equal to 2x1 minus x2 plus x3, subject to 2x1 plus x2 minus 2x3 less than or equal to 8, then 4x1 minus x2 plus 2x3 more than or equal to 2, and 2x1 plus 3x2 minus x3 more than or equal to 4, with x1, x2, x3 more than or equal to 0, non-negative. All variables are non-negative in nature. Okay. Now see, it's a maximization problem, so we handle it the way we did the last problem. So your optimality criteria will be governed by all zj minus cj's. If they are more than or equal to 0, optimality is attained. Okay. But see, this constraint is less than or equal to type. So what do we need? We need a slack variable here. Okay. But then these two are more than or equal to type. So both of them will have a surplus variable. But slack variable comes with an addition and surplus variable comes with a subtraction. Okay. So when you rewrite this problem, it will be something like, again, I will not write anything with regard to slack and surplus in the objective right now, but your first constraint will talk of an addition of a slack variable x4, and its contribution to the objective function will be 0. Okay, the coefficient will be 0. So we add it the way we were doing it, right? Similarly, now see what will happen to the second constraint. Your second constraint will be 4x1 minus x2 plus 2x3. Now see, we need to subtract a surplus variable. Okay, so I'll have a minus x5 here and accordingly a 0x5 here. But I need, that's, as I said, surplus variable never comes alone. It has to come with an artificial variable a1, okay, which needs to be added because I need the coefficient 1 in the matrix A, okay. So I'll have a1 here. So a1 itself says that it's the first artificial variable equal to 2, right? I'm not writing anything here. We'll talk of it later on. Then the third constraint similarly will be 2x1 plus 3x2 minus x3. Now again, we have to have a surplus variable x6 with coefficient 0, but I need another artificial a2, where of course x1, x2, x3, x4, x5, x6, even your artificial variables, they are all non-negative. Okay, now see, we are saying that A1 and A2 have no as physical contribution to the problem, and we want them to leave the basis at the earliest, but we also want to guarantee that they never come back. Okay, and because the simplex algorithm needs a CJ corresponding to A1 and A2 both. Then only we'll be able to calculate our Zj minus Cj for them also. Now we say that the most negative Zj minus Cj enters, and and the ratio helps us to leave it. Okay, so what we do is to make it positive, and so large a positive number that it never enters the basis again. See, basis को enter कब करेगा? When your Zj minus Cj is less than or equal to 0. Now, if somehow we manipulate the coefficients of these artificial variables and we make them so large, that means we make them so large and positive, so what will happen? They will never enter the basis again. So what we do is, in the maximization problem, we add their coefficients as minus m both, because when you compute Zj minus Cj, this minus m will become plus m. Okay, so what will happen is that this m is an unknown quantity. We say that where m is a very large number in comparison to what? So say in comparison to these single digit coefficients, 100 is also large. Okay, but if say supposing your problem deals with coefficients which themselves are 4-digit numbers, then your m has to be taken appropriately. So that is why instead of giving it a fixed value, what we randomly say is that m is a very large number, depending upon the size of the problem. So that's why whenever you use a software to solve linear programming problems, you have to define a value of m. And as I say, normally depending upon the kind of problem, we give the value of m. Like in this case, I would say, okay, let m be 100. Okay, so in case the coefficients themselves were large, I would have taken m to be say 10,000. So that is also large. So that means this large is left again to the person who is solving the problem, because he or she can choose the large number accordingly. What large number do we actually want? Okay, so this is how the objective function changes when we are dealing. See, that's why this is called as the Charnes Big M method, because this m is big. It's a very large number. It's a big number. Okay, now is this clear? I just need one response, that is this point clear or not? Any one of you can just unmute and say yes. ठीक है कि नहीं?
Yes, ma'am. Clear है.
ठीक है, चलो फिर आगे बढ़े ना. Okay. Now, once we have this, we have formulated the problem in the standard form. Now comes your what? Table 0. As I said, your simplex method will not change. This is your initial table now. So again, ये calculations, so now you will have to do simultaneously with me, and then we can go ahead. Say that means we are going to have our xb's here, you know, b, 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 and we have our cj's here, x1, x2, x3, x4, x5, x6, but now you also have a1 and a2's. Okay. Now the coefficients here will be 2, -1, 1, 0, 0, 0, but here I'll have minus m's, because these are the coefficients of the artificial variables in the objective function. Okay. In case we have a minimization problem, then we take it as plus m. Okay. And your, sorry, entries will now be 824 when you have 242, 1 minus 1, 3, then minus 2, 2, minus 1. X4 is 1, 0, 0, but X5 is 0, minus 1, 0, and X6 is 0, 0, minus 1, right? So they do not contribute to the identity part, right? However, A1 is 0, 1, 0, and A2 is 0, 0, 1. Is this okay now? Right. Now, what are your
Yes,
basic
ma'am.
variables? Your basic variables are now
X4,
X4, A1, and
A2.
right. And what are the coefficients here? 0, minus n, minus n. Okay, na? Now see what, now you will see the difference. We have to do the computations, we have to compute z, we have to compute zj's, and we have to compute zj minus cj's. Okay, now observe one thing. Your z in this case is what?
Minus 6M.
Minus 6n, right? Now see, in the earlier cases, rz was always 0. We started with that point 0. Now with minus 6n, and m is what? A big number, say 100. So how much is your z? Minus 600. So it is even less than 0 that you have started with. Okay. And accordingly, at every stage, when you move on, this value of z is going to improve. Your problem is a maximization type. So definitely the value of z will increase with every iteration. Okay. Now, but then your zj's will be different now. They will not be 0 now. See, this will be what? Minus 6n. You know?
Yes, ma'am. Minus 6M.
This is 0. Now this is m minus 3m. So minus 2m. You know? Then minus 2m minus 3m.
Minus M.
Minus m. I'm sorry. Then this is 0.
M.
M,
M.
m
Minus M. Minus M.
minus m minus m. Right? And accordingly, your zj minus cj is 6m minus 2 minus 2m plus 1 minus 3 minus m minus 1. 0 m m 0 0. यही आ गया ना. Now, of course, because of m and because of minus sign also, this is definitely not an optimal solution because you have so many negatives zj minus cj's. Okay. See, the only thing is that this is 0, this is 0, this is 0. But then this is, and just a minute, girls. 1 minute. But then see, this m and this m, they are positive. So we have taken, remember, we have taken m to be how much? 100. Because there, that means these are going to be plus 100. So definitely ये तो positive होके तो ये तो enter करेंगे ही, right? Now we have these three negatives Hj minus Cj's. So out of them, which one will enter? The most negative. So the most negative choose करने के लिए write m100 and give the values here. So it's like minus 600 minus 2. So it's almost minus 602, right? This is minus 200 plus 1. So minus 199. This is minus 101. ये values are गई ना. So out of these, which one is the most negative? Minus 602. So that means what? X1 enters the basis. Okay, now the remaining procedure again remains the same. That's what I said. We are not doing away with the simplex algorithm. Now compute the ratios. So it's going to be 8 by 2, 2 by 4, 4 by 2. So 8 by 2 means 4, half, and 2. So which one is minimum? half. So that means what? A1 leaves the basis. So what is your key element now? 4. Is this okay? Now, the point is that if A1 has left the basis now and this ratio was half, and because of this coefficient here, the corresponding value of Zj minus Cj in the next step would be so high that it will never be able to enter the basis again. So what we can do is, once an artificial variable, see, we cannot do this with slack and surplus. We can do this only with artificial. Once an artificial variable leaves the basis, since it is never going to re-enter again, so in the next iteration, I can remove this column from my table of A1. It's not required anymore because it will not come back. It has become a non-basic variable and till the end, it will remain a non-basic variable. So I don't need its value. I don't need its role is over. Its job is over. Okay. So move to the next table as you have done earlier. Is that okay?
मैम इसका मतलब जो हमारे आर्टिफिशियल वेरिएबल्स A1 A2 हैं, अगर एक बार बेसिस से लीव कर दिए उसके
हम्म,
बाद हम उनको कहीं भी यूज, मतलब कि उनका कोई रोल बचेगा ही नहीं।
नहीं,
ओके मैम।
उनका काम सिर्फ हमें इनिशियली एक सोल्यूशन देना था, वो देते ही उसका काम खत्म हो गया। अब उसको बेसिस से निकल जाना चाहिए।
ओके मैम।
So now move over to table 1 जैसे पहले किया। अब टेबल 1 जब बनाओगे तो अब क्या करेंगे, हमारे क्या हो गए, x4 x1 a2, यही 3 रह जाएंगे ना। And when you make the columns here, x1, x2, x3, x4, x5, x6, अब मैं a1 नहीं लिखूंगी, मुझे चाहिए ही नहीं, because वो आएगा ही नहीं बेसिस में कभी वापस। So gradually what will happen, these artificial variables will be removed from the table itself. So this is the advantage of Big M method, that they will not create problems for us later on also. तो एक बार उनका काम खत्म, उसके बाद we can remove them, we can work without them also. So no need to make that. जो artificial variable basis से चला गया, we don't need the required column, the relevant, the column related to that variable. उसके बाद हम of course या इसका कोफिशिएंट अभी भी -m रहेगा, no, and x4 x5 x6 0 थे, वो रहेंगे. Then it was like 2 minus 1 1, that will remain, right? Similarly in this table now your coefficients will now be 0, x1 का कितना है 2 and -m. So you will see इस -600 से बढ़कर कोई और वैल्यू आएगा अब यहाँ, right? So since your key element was 4, so I think it will be 1/2 now, है ना? And इधर 1 आ जाएगा. So now you can complete the calculation जैसे पहले करते थे हम. A2 will not change now. Now again do the same elementary operations as we were doing earlier and then move on. Is that okay? अब इसके आगे कंप्लीट कर लोगे? इसके आगे तो वही सिंप्लेक्स मेथड ही चल रहा है जो हम पहले चलाते आए हैं.
यस मैम।
ठीक है ना, अब आगे तो फिर कंप्लीट कर ही लोगे अपने आप इसको. चलो ये करो. अच्छा, इन केस यू हैव इक्वालिटी कॉन्स्ट्रेंट, अभी मैंने उसकी बात नहीं करी ना, हमने अभी सिर्फ मोर देन और इक्वल टू टाइप रखा था. ठीक है, इन केस वन ऑफ द कॉन्स्ट्रेंट इज इक्वालिटी, ये वाला. ठीक है, सो इस केस में हमें ना तो स्लैक चाहिए और ना ही सरप्लस चाहिए, बिकॉज उनका कोई काम ही नहीं है. देयर इज नो स्लैकनेस, no and there is no surplus of a particular resource. So in this case only artificial is introduced, और कोई वेरिएबल हम उसमें ऐड या सब्ट्रैक्ट नहीं करते, but we only introduce the artificial variable in case you have an equality constraint. So that, and normally you will see कि वैसे तो depends upon the problem, which artificial variable leaves the basis first. So that will vary from problem to problem. But with equality constraint, we will not have any slack variable, we will not have any surplus variable, but we will introduce only the artificial variable. Is this okay? Then there can be, and I'm just giving you an introduction to that, but then there can be a situation. See, अभी तक हम क्या कर रहे थे? We were assuming that all our variables are non-negative in nature. ठीक है? But sometimes what happens is that even the decision maker doesn't know what kind of values can that variable take, whether it can take positive values, whether it can take negative values. वो एक पैरामीटर ही ऐसा डिफाइन हो जाता है where it is difficult to ascertain whether it will always be non-negative or not. So in that case, what we do is we say that a particular variable is unrestricted in sign. That means that particular variable can be positive, that particular variable can be negative. So it is unrestricted in sign, right? But the problem is that your simplex algorithm only handles problems or only allows us to solve problems which are non-negative, which satisfy the non-negativity restrictions as well. So in case your problem is such that a particular variable is unrestricted in sign, then we have to make some modifications. In the sense that, say, supposing you have, okay, write down this problem and then do it as a homework. Supposing your problem is to maximize z equal to 5x1 minus 2x2 plus x3 subject to 2x1 plus 4x2 plus x3 less than or equal to 6, 2x1 plus x2 plus 3x3 more than or equal to 2, and x1, x2 more than or equal to 0, but x3 we write it as UNS, unrestricted in sign. Okay, so we are given that x1 and x2 are non-negative, but x3 is unrestricted in sign. Okay, so what we do in this case is, with an unrestricted variable, I cannot directly apply the simplex algorithm here because I need it to be written in the standard form first. And standard form says that non-negativity restrictions should be satisfied. Okay, so to go ahead, what we'll do is, okay, this is clear. You will have a slack variable here. Okay, एक x4 आ जाएगा. And in this constraint, you will have a surplus x5 plus an artificial a, right? That is okay. The constraint part is taken care. Now, how to handle x3? What we do is, we say let x3 be written as x3 dash minus x3 double dash, where both x3 dash and x3 double dash are more than or equal to 0. कर सकते हैं. Any number can be written as a difference of two non-negative numbers. कर सकते हैं कि नहीं? Say supposing 7. I can write it as what? 8 minus 1. Right? Or if I have say minus 3, I can write it as 2 minus 5. That means both the entries here, they are non-negative, or in fact 3 minus 3 I can also write as 0 minus 3. Are you getting? 7 I can also write as 7 minus 0. So every number can be expressed as a difference of two non-negative integers, or rather two non-negative numbers for that matter, right? So what we do is, we replace the variable which was unrestricted in sign with two variables which are non-negative. So what have I done? I've simply added a variable here, but now all my non-negativity restrictions are also being satisfied. Okay, so this is the change that we are going to make in the variables. We'll replace the variable which is unrestricted in sign with x3 dash minus x3 double dash, where both x3 dash and x3 double dash are non-negative in nature. Okay, and now proceed on because all your variables satisfy the non-negativity restrictions. So your simplex algorithm can be very well applied here, right? So what happens is that once you solve in this manner, in the end, you will realize no matter what kind of problems you have, you will realize that never ever would it happen that in the optimal solution, both of them are present in the basis. See what is happening. If in case your x3 was to be negative, so what will happen is that x3 dash will be a non-basic variable. तभी तो वो zero होगा. So what will happen? Your basis will only have x3 double dash. So as a result, which value will x3 take? 0 minus whatever is the value. Right? Similarly, if x3 were to be positive, then accordingly x3 double dash will be non-basic. And so the value of x3 will be same as that of x3 dash. So it is again, the algorithm is so well designed that never will it happen that you will have both of them, x3 dash and x3 double dash, both in the basis. One of them will always be a non-basic variable. Because non-basic का मतलब ही यही है कि the value of the variable is equal to 0. So accordingly, you will get the value of the variable which was actually unrestricted inside. So not just non-negative, we can handle problems with the help of simplex algorithm. We can handle those problems also where the variables are unrestricted inside. Is this clear?